Hi, back to our Basic Electronics Series 4. What I'm going to talk um, in this YouTube is going to be about our diodes and diodes application circuit. But first, let me wrap up what I left off of C and L circuit from the last time. Let's take a look at resonant circuits and active filter. We use the L and C together for circuit applications. That's what we call active filter. You take a look at the plot, or you start from the circuit here. When you have C and L in parallel, and you also have R in series here. You have apply input voltage and you expect V output. And for your V out, you are simply look at this one as the voltage divider when you have only your resistor, right? And then you have our total impedance, so you can apply the voltage divider to find V out. So your V out is direct proportional to our Z total here. But what look something look strange here, because there you see the impedance is what 1 over j omega c, and when for the frequency here, let's start the frequency. This is low frequency, and you move to the high frequency from the left to the right. And for your C, we're talking about the impedance, or Z of C, because C of Z is 1 over j omega c. When you have low frequency, the capacitor impedance become high, correct? And what about the high frequency? The impedance of capacitor become low. But for inductor, you know your ZL equal to what? J omega L, correct? Is the direct proportional to our frequency. So when the frequency is low, the impedance of inductor is low, and for the high frequency, the impedance of inductor is also high. So it seems to be work on a different way, right? When you connect C and L like this one. Okay, just let you analyze the circuit. But for this one, we're going to talk about the resonant circuits. Let's see, how the resonant circuits work. When you have C and L in parallel, and you know that your V out is proportional, direct proportional to your Z total. And for your Z total, it simply come from C in parallel with L. So 1 over Z total equal to 1 over ZC plus 1 over ZL. And you plug in, this is your ZC and this is your ZL. You rearrange the term. Finally, you have Z total become J over 1 over omega L minus omega C. And for the case if your Z total become infinity, this means your V out is going to be infinity as well. This happens when? Because your Z total is equal to this equation here. It's become infinity when your denominator is become 0. That means your 1 omega L minus omega C, they are equal, or your omega equal to square root 1 over LC. or F0 equal to omega over 2 pi, and your omega is the square root 1 LC. And finally you have F0 become this term, 1 over 2 pi square root LC, and this is what we call resonant frequency here. And give you the output become the high peak, same as the plot here. This is the V out over in and frequency here, and the resonant frequency here at the peak. This is F0 as we derive from this equation here. You have F0 equal to 1 over 2 pi square root LC, and you also have our Q factor that's equal to F0 over delta F at 3 dB point. As we worked out before, how do you find delta F 3 dB? Well, from the top, and you drop down like 3 dB in case of the gain or V out over V in the unit of decibel. You drop this down to be what? How much? 3 dB, right? You find the 3 dB point is going to have like 2 points on the left and on the right of F0, and you can find delta F 3 dB. So it's become the space here, and that's how you define Q factor. It's actually it's measure the sharpness of the peak and use application of audio frequency and radio frequency. Okay, now let's pay attention to our Q factor. Of course, when you have this small number here, this means our Q factor is going to be very large, right? So it will be very sharp, I mean the peak. And if Q very small, it's not going to be flat, right? So this is represent Q or what? Small, correct? Because we have this one very large. So I put this one as small. And if you have very sharp curve here at resonant frequency, this is represented by Q is very, very large. Okay, just for your information. And now also take a look at what I have in here. Okay, so let's take a look at the Q factor here. But I'm not really proof for this one. You might want to work out, try by yourself. For LC resonant circuit or parallel RLC circuit, your Q factor become omega 0 multiplied by R and C. Now take a look at another circuit of LC. This is what we call notch filter circuit. It's going to be opposite of the resonant circuit, because at the F0 or this frequency, which is equal to 1 over 2 pi square root LC, your V out drop going to be 0. The way they connect the circuit is look like this one here. You have R, it's just the same, but instead of connect L and C in parallel, we do in series. and you do the same thing, your V out simply become direct proportional to Z-total. This means ZL plus CC. And when you use the voltage divider, V out equal to V in multiplied by this is Z total divided by R in series with the Z total, which is become R plus J multiplied by omega L minus 1 omega C. And if you want to make this one to be 0, that means you also do the same thing. This means your omega L equal to 1 omega Z, and you end up with F0 equal to 1 over 2 pi LZ. You derive exactly, like from the resonant circuit. So our total Z total becomes 0 at F0, and for this case Q factor for a series RLC circuit, because this we call RLC circuit, right? But that one is like in parallel. Q equal to omega zeros multiplied by L. Okay, so that's what I wrap up what I left off of the application of C and L. There will be much more application circuits for C and L. Okay, so next what we're going to do, sorry, this is what missing is the divide by R. Okay, the next electronic device that we are going to talk is the diode, which is very important electronic device. Just for many applications. It's very simple device, but play a very important role in electronics. You're probably familiar with the circuit. That's what we call rectifier, just like this one here. We use that to convert AC signal to DC signal, and we can also use the diode as switch. And you know that the diode allow the current flowing into only one direction and not allow current flowing into the other direction. So let's start with the symbol. This is the diode symbol. You have the anode and the cathode, and this is p-n junction. This is p-type, and this is the n-type semiconductor. To connect the circuit, if you connect the circuit like this one here, you have the positive apply voltage to the anode and negative supply voltage to the cathode. This is what we call the forward bias. And if the voltage across the diode equal to 0.7 or greater than that, the diode start to conduct, or it's become just like closed switch or closed circuit. When I say 0.7 volt, usually is when you use the silicon diode. This can be different, okay, depending on material that you use for the semiconductor material that you use to make a diode. And if you connect the other way around here, you have the negative on the p side or on the anode, and the positive on the cathode or on the inside. This is what we call a reverse bias, and the diode is not conduct, as no current can flow through the diode. It's become just really like open switch or open circuit. I'm not going to get into the detail of p-n junction or a semiconductor, because we're going to talk about the diode itself and the applications. Now take a look at the IV curve of the diode here. You have our V, and this is on the positive side. You call it the forward bias, and negative side of the voltage we call is the reverse bias. And the curve look like this one here. When you start increasing forward bias voltage, at some point the diode start to conduct. As I say, for a silicon diode, let's say if you start from 0.7 volt or greater than that, you will have the current flowing through the diode, and this corresponds to the diode equation here. ID, the current flowing diode, does depend on VD, or the voltage across the diode, equal to I0, or the leakage current, usually in the order of nanoamp. Is very small current, multiplied by exponential VD over KT. VD is the voltage across the diode, K is the Boltzmann constant, T is the absolute temperature in the unit of Kelvin, and -1. And if you were do the reverse bias, you increase more and more negative bias voltage. At some point, your diode is going to break down, and you have the infinite current flowing through the diode, and you cannot use the diode anymore. And if you also look at the equation here first, it's work out very nice. For let's say we across the diode becomes 0, this term become 1, right? Exponential to the 0 equal to 1. 1 minus 1 is give you 0, so you don't have any current flowing through the diode. But when you are increasing the forward bias, this term is become bigger and bigger, and this term is much larger than 1, so you can ignore 1. So after that, your ID viewer corresponds to VD as in the term of I0 multiplied by exponential VD over KT. Now for the reverse bias, you have VD become negative here, so this term drop is become very small. You end up with negative I0. So that's why you have the leakage current here. This is your I0. It's very small number in the range of nanoamp. And another point is I want to mention here is that the plot, the relation of IV or of the diode is not linear, right? But if you take a look at the Ohm's law, R equal to IV over I. Since you plot between I and V, the slope of the plot simply become delta I over delta V, right? actually is become 1 over resistance of the diode at each point. So you see when you don't have a constant slope, because this is not a straight line, a different ID, you will have a different slope or different resistance of the diode, or that's what we call our forward. So this is one of interesting characteristic of the diode. Okay. So that's why I wrote down is the diode is the nonlinear device, and Thevenin theorem cannot be applied to the diode because you have the different R when you have different I here. Okay, so this is the basic concept of the diode. Now take a look at some applications. The first one is rectification circuits. As I mentioned to you before, that many people are familiar that the diode, you use that for rectification circuit, does convert AC signal to DC signal. That's used in many electronic appliance, because you need the power supply, right? A DC power supply. So that's why sometimes they call diode as the rectifiers, because you use that in a rectification circuit. Take a look at the first circuit here. You connect the AC input signal in series with the diode, and you have a load at the output. This one we call half-wave rectifier circuit. When you have your input signal, let's say in a sinusoidal wave, that's on the red line here, when you pass the signal to a diode, you will have the output look like the blue line here, or you just pick up the positive signal and ignore a negative signal, or not allow the negative signal to pass to the diode. And it's agree with the property of the diode as I mentioned here. Correct? Simply it's going to work as an open circuit or open switch. So you are going to have only the positive signal here at the output. Now take a look at the full wave rectifier circuit. You have 4 diodes, and you have R load at the output. The output waveform is going to look like this one here. It's also pick up the negative input signal, but it turned out that it will take the negative input signal and show up at the output, but in the form of positive signal. You have like 180-degree out of phase when you have the negative input signal coming in. And if you notice, you also have the space between the signal here, and that's because you have the voltage drop across the diode when the diode is on here. So simply it's pick up both negative input signal and positive input signal to show up at the output, but always gonna show up as the positive output signal. That's how full wave rectifier circuit work. Okay. But for application of our DC power supply, you can see that what we need is, like, we want the smooth DC output voltage. But look at this one. You don't have a smooth output signal yet, or you don't have like close to DC signal. So you need the help of the filter circuit, and how we discuss next. And this one I also put on my YouTube on rectifier circuit using the PSpice simulation. You go back over there, you will see your clearer pictures. Okay, so to obtain the DC output voltage, you need a filtering circuit, and this is the filtering circuit. Actually, it looks like just like a low pass filter circuit, because you have C as the output. As I mentioned before, your output is direct proportional to the impedance of capacitor, and the impedance of capacitor here is become negative J over omega C. When you have high frequency, your voltage, output voltage drop, because this term become very small. It's opposite of the frequency. You have high frequency, you have low impedance. You have low frequency, you have high impedance. So this filter out the signal after the signal from full wave rectifier circuit on the previous page, or of what I mentioned earlier. And let's take a look at the ripple voltage calculation. First of all, let's take a look. What is the ripple? That's from the full wave rectifier circuit. When you pass the sinusoidal signal, or the input sinusoidal signal, to the full wave rectifier circuit, you end up with the output voltage look like this one, the blue line here. So to smooth the signal out, okay, we want the straight line here, or the DC signal. When you want to have a let's say very close to a straight line here as the DC voltage, you need to connect, just like I mentioned before, your R and C, or low pass filter circuit, right after your full wave rectifier circuit. And this is what we call ripple. Okay, just gonna go around here and go here. It's not really a straight line. Okay, but of course you want to have the output voltage as this DC voltage, like this straight line. But if you take a look at closely, you still have ripple. This is what we call ripple. Okay, so at your filter circuit, you have C at the output. So your IC from equation I equal to C dV by dt, and this is the, you can write this one dV as delta V equal to I over C, and then multiply by delta T, where delta T is approximate to be 1 over frequency. The frequency here is the ripple frequency, or for full bridge rectifier you can use the delta T equal to 1 over 2 times of the ripple frequency. And this is for the half wave here. You bring up the delta V, you know, here, so delta T you approximate to be 1 over F for full wave, but for for half wave and for full wave you represent delta T equal to 1 over 2F, so you end up with delta V equal to this equation here. When you have ripple max equal to 0.1 V peak to peak, and you want I load max to be 10 milliamps, and frequency equal to 60 Hertz, just for example, so you can calculate for delta V. Okay. You can calculate for capacitor in case you want to design the circuit. You know, you have R and you have C here. Okay. Now take a look at another application. Actually, it's still work on DC power supply. Now for DC power supply, you know exactly that you need to AC input signal here. That's the input of the transformer, which have the primary and the secondary. And I already talked about transformer, you know, before. I don't know, in our basic electronic YouTube series 2, probably. So there's another type of transformer. This is what we call a center tap transformer here. You break apart, you can use up you know, there's 2 parts of transformer on the secondary side. This one I just mentioned is the, if you want to get the, if you use like, this is the full wave rectifier, right? When you have input signal coming in, you have the output signal look like this one. Long time ago, people trying to use center tap full wave rectifier, which means they don't use this one. They just use usually center tap transformer. The problem is that when you have like use 2 part of transformer, your intention is for this part you want to pick up the positive input signal of the sinusoidal, and this part you want to pick up the negative sinusoidal, the input sinusoidal. But the problem is that when you break, you know, the transformer here in half, you have like your I equal to V over R. When your R drop, you have the current here increased, you know, to be twice, and each part it's not working at the same time. When you have the positive input signal coming in, this part's working, but this part doesn't work. And when you have the negative, sinusoidal coming in, this part stop working and this part working. So it's only like 50%, of the secondary side of the transformer here working. And the main part is that you have a double current here. And if you compare to power P equal to I square R, what happened? When you have double current, and this term is square, so you have 4 times of heat. So in practical, it doesn't work. So that's why we use the full bridge rectifier here instead. And that's we call, as I mentioned earlier before. Okay. Now we also use the transformer as the split supply. What does it mean, split supply? Split supply is give you both the positive output voltage and the negative output voltage. So that's why I have the output look like this one here. Just only one full bridge rectifier. So they work at the same time here, even you break down, the transformer on the secondary side. And you have sometimes we call a dual. Dual is mean two, right? Dual DC power supply here. You have positive and negative. So this still become an application of diodes. Another diode circuits is the voltage multiplier. The voltage multiplier is mean you want to increase your output voltage. And sometimes we call a voltage doubler circuit. You double your output, voltage, but you're going to have a ripple frequency become double as well. Okay, I'm not going to explain, the circuit. It's just like tell you that we also have another circuit when you use the diode. We call the circuit is the voltage multipliers, and the way to connect your diodes look like the circuit. Now let's take a look at signal rectifier circuit. The way you connect the diode, you have your capacitor and you have R1 and you have R2. So the first part here we studied before, it's look like a differentiate circuit. What does this mean, differentiate circuit? The differentiate circuit is mean when you want to have V out here, it's simply you differentiate your input, right? Signal that's coming in. Okay, this is directional proportional to this one here. So when you have the square wave as the input signal coming in, you end up with the output signal after the differentiate circuit like this one here, because it's just like you differentiate, at this point you go straight here, you have like spike, but when you have this part of the square waves coming in, when you differentiate you have 0, so you don't have any signal right at this point. And for the falling edge, the slope become negative, so that's why you have negative spike here. So it's repeat itself And after that, this one become the input of your diode here. And as we know that the diodes is only allow the positive signal to pass through, so you don't have this part of your signal at the output. So finally you have the output signal look like this one. And just keep in mind that since the diode to be able to conduct the voltage across the diode have to be is greater or equal to 0.6 in this case. This may different, which is I mentioned before, it can be 0.7 for silicon diode. This is like peak to peak. But sometimes they use the Schottky diodes because they have their much less than forward voltage across the diode to be able to conduct. So to solve the problem here, if you have input signal level less than 0.6, you never be able to turn on the diode here, right? So what happens if we still want the input signal here to show up at the output? The way they do that, the way they correct the problems or modify the circuit is that you just simply connect another source, to the circuit. Let's say 5 volts here, and you have the voltage at this point to be 0.6. So it seems like you already have like 0.6 volt, and or you have a closed circuit ready for your input signal to come in, right? So it seems like diodes already on, so just wait for the input signal to come in and you will have the output signal, and this still become the differentiate circuit. Okay. The next one is the digital gate or digital logic. Let's say this is for the power backup application. This means that when you have electronic appliance that require the supply voltage between 12 volt to 15 volt, and usually you get the power supply from your house. And what happens if you have the power down, so you cannot they have no supply voltage to electronic device? Sometimes you want electronic device continue working, for example like clocks. So what we need to do is need to have the backup battery here, and you're going to use the diode to make the system work. When you have no power, you just use the power from battery. Okay, that's why we call digital logic here. So what we do is we connect the diode here. Let's take a look at this. I have let's say I have input A here and input B here, and this is output. So I have like 4 combinations of input, right? This becomes 0 0 1 1 for A, and B 0 1 0 1. So I have 1 2 3 4 combinations. And your output, this is since it works as the OR gate here. You have our output to be 0 when you have both input to be 0, right? And the rest, you have output to be 1 because you have one here, one here, one here. So for this one, if you have no supply at all, you have no battery at all, you have no supply, voltage to your electronic devices, right? So it's become 0. And what about, let's say, for this one, you have no DC power supply, right? Because your input is A here, it's 0. But you have the supply from battery. When you have 12-volt battery here, this is the forward bias across the diode here. So the diode start to conduct, and that's why you have 12 volt as the supply voltage to your electronic device, and your output C is become 1. That means you have supply. Now for you have a supply voltage to be 1, or at A to be 1, so you mean you have the supply voltage, so the diode start to conduct, and you have supply voltage to your electronic devices, and that's why you have the output C become 1. So what about if you have both DC power supply and battery? Well, in this case it will pick up the higher voltage. So earlier the electronic devices get the supply voltage from DC power supply, as in the diagram here. Now think about, at the same time, if you want also to be able to charge your battery, how do you modify the circuit? Just think about it. Okay, let's just give you a hint that you need to add another diode, but I'll let you work out how the way to connect the diode to the battery and to the DC power supply. Okay, another application is we call diode clamps. The diode clamps limit voltage level. How does the diode clamps circuit limit the voltage? Let's say if you have the V input coming in here, and you have the diode connect to the supply voltage 5 volt, and this is your V out. Of course, the voltage drop across the diode here. In case of silicon diode, you know that V drop here simply becomes 0.6 volt, right? So when you have the difference of the voltage, this has to be forward biased across the diode. That means you need to have this part have the higher voltage than 5 volt. So this is simply become a 5 plus 0.6 volt, and it end up to be 5.6 volt. That's how we call like diode clamps or limit voltage level. It's not allow like the output voltage here to be higher than 5.6 volt. If you have higher input here, voltage still drop here 0.6 volt anywhere. So you cannot change output. Your output still become 5.6 volt, but you have more current flowing through here, right? Because you have higher input level. And also this one, you connect your diode in the opposite way around here. So you will limit your V out to be between negative 5.6 to 5.6, and you already understand about this part here. So what about this one here? This one have to be what? this is 5 volt. You want this one to be so this one have to be actually, you think about it, V minimum have to be negative 5.6, because this is going to be when it's on, it have to be a voltage across this one to be 0.6. okay, let you think about it. So your V out is going to be in the range of negative 5.6 plus 5.6. This is what we call diode clamps, and this limit voltage level. Okay, before I finish this the YouTube, let's take a look at inductive loads and diode protection, because this is get involved in also the L, and also you can bring up the diode, to solve the problem. Okay, what does this mean, inductive load? When you're talking about the inductor, you have equation for inductor, the voltage equal to L multiplied by di by dt, or the change of the current, respect to time. At the start, when you have the closed circuit here, you have the current flowing through the circuit, right, passed to inductor. But when you open the circuit here, you have no current flowing, so your delta I, it used to be you have I, but you end up current to be 0 in the short period of time. This is delta t is very small in a second here. So what happened? From the relation, you have V become a very large number, and you have problem, and this is what we call inductive kick. So for the relay application, you don't want this one to have problem, to create some problem. So what you can do is you just connect diode in parallel. That's why you see a lot in relay circuits. That means when you have a very high voltage, you need to bypass your current flowing through the diode here, so you solve the problem. But just to make sure that I here have to be in not over than specification limit of the diode current here, otherwise you also have another problem as well. So that's why I say diode must be able to handle this initial current IL when you open the switch. So let's take a look back again. When you have the switch on, you have current flowing through here, the inductor, and then you also have the higher voltage than this point. So the diodes become reverse biased, correct? And then this is just like open circuit here. Now when you have open circuit here, you have no current here, so you have the voltage build up, and you have the higher voltage here compared to this one, so the diode become just like the closed circuit, or start to conduct. So you have the current bypass flowing to your diode here. That's how it's work to sort of inductive kick. Okay, so that's all I want to talk about the basic electronics in the YouTube 4.